Okay, this is going to be the video for Calc 3 section 15.3, which is double integrals, but this time over general regions instead of rectangular regions in the domain. So let me go ahead and present the notes and we'll get started. Okay, so so far what we've talked about, we've defined what a double integral is, right? And then we said if you have a rectangular region in the domain like this that's established by numbers, like let's say from 1 to 5 in the x direction and from 3 to 4 in the y direction, then you can take the integral from, let's see, from x is from 1 to 5, right? And y is from 3 to 4. And because these are just numbers and there's no dependency, then you can choose to either do x as the inner integral and y as the outer, or the other way around, right? There's no dependency, so you're free to choose whichever you think is best, right? And they'll both be about the same level of difficulty, right? But if the region in the domain is not rectangular, so these are all domain regions over here, then you've got a different issue. Let's say that you have some region that's defined like this, okay? And that means that you could still represent that region as having some numbers associated with it in the y, like no y is less than 3 and no y is more than 4, let's say, right? But the position that x is changes for different y's. In other words, there's a dependency between the x values and what y you happen to be on. So for this particular red slice here, right, the x value is established by some function of y. And the upper boundary, the ending limit of integration, is also established by probably a different function of y, okay? And so in that case, then you would, if you're deciding to integrate in the x direction first, one thing that we'll always ask you to do is always graph the domain, okay? And the reason for that, let me see if I can clear up a problem here with my... We want to always graph the domain because we want to indicate, well, which direction are we integrating over first? So this would be, for example, the x direction first. Okay, I'm going to reopen my presentation here to stop a problem with my pen. Okay, and then let me represent. Hopefully that'll correct this problem, because sometimes my pen gets in this mode where it doesn't write properly. All right, so we said we're going to always graph the domain. Oh, still there. Oh, well, we'll just work around it. We'll always graph the domain, and then I'm going to indicate with an arrow which variable I'm integrating over first. In this case, I'm integrating over x's first, so this is the x direction. And that means that my starting and end point might depend upon which y slice I'm integrating, right? So that means my limits of integration will typically be functions of the outside variable. There's a dependency there, right? And then there's other regions like this one where maybe it makes more sense to have these boundaries be numbers, like from 2 to 4 or 2 to 5 or something like that. But then you want to integrate in the y direction first, right? So if we're integrating y, that means that our dy is here, right? But when we establish the limits of integration, we're not going to have constants like we do up here. We're going to have a y which is a function of which x we're currently on, and then a stop limit of integration or ending limit of integration that's also a function of x. So typically there'll be functions here of the outer variable, okay? And you can just see that the rectangular area is just a special case of that, where the inner functions here are just numbers instead of functions. So they're constant functions, right? The outer integral will typically always have numerical limits of integration, but the integral limits of integrations for the inner integral will typically be functions. All right, so here's an example. Let's say that we want to integrate over a region at the function x squared plus y squared. And the region is defined as x stays between 0 and 2 inclusive, and y is between the curve x squared and 2x. So you could say that there's a boundary here of the curve y equals x squared and y equals 2x on this side. Okay, so the first thing we'd do is graph that domain, right? Y equals x squared is a parabola, right? And then y equals 2x is a line. And so if I wanted to figure out, like, where are the kind of edges of these, typically we find the intersections. In fact, whenever I have two functions, that'll pretty much be the first thing that I will always do is find the intersections. So y equals 2x, y equals x squared. If you set the y's equal to each other and then solve by getting everything on the left and factoring, that occurs when x is 0 and x is 2. So I know that this region is going to be bounded from x is 0 to x is 2. And then in the upper, the y dimension, if we plug this back into one of these functions, you get 0 for y and 4 for. So y equals 0 and y equals 4. So everything in the domain region that we're covering is in this little region, 2 to 0 and 0 to 4, except it's not the entire rectangle, it's only a portion of that. Okay. So then when we get ready to do the double integral, we have to decide which one to go first, which variable to choose first. So we could draw an arrow in our sketch of the domain that goes upward, which means we're integrating in the y direction first, which would put y as the inside variable for the integral. Okay, and so then we would go ahead and do the integral, but we'll have to establish what the boundaries are. So this lower boundary here is the curve y equals x squared. If you solved it for x, it would be x equals square root of y. This upper curve here is y equals 2x, which could also be written as x equals 1/2 y, right? And since we're talking about integrating out the y, that means we're going to have to leave everything as a function of x, right? So I'm going to have to solve for these boundaries as y values, right? So the y value here will be given by x squared. That's where we start. And then we'll stop at the end of the arrow when we get to y equals 2x. So the boundaries would be y equals x squared. So x squared is the lower boundary and 2x is the upper boundary. And then we'll have to then integrate, after we're done integrating for that, we have to cover all of the slices, right? And so those start at an x value of 0 and end at an x value of 2. So the outer boundaries are 0 and 2. So first you have to use your picture of the domain, put an arrow on it to indicate which direction that sets, which is the inner variable, and then typically you'll use function curves to get the limits of integration. Now the actual integration part, right, first we treat y as the variable, so x squared is a constant, so the antiderivative is x squared times the variable y, and then y squared is 1/3 y cubed. But then when we do our fundamental theorem, we're going to be plugging 2x into this first and then subtracting what happens when we plug x squared in. So this is the function with 2x plugged in for the y, and also here, right? And then this is that same function with x squared plugged in for the y, and 2x first and then x squared plugged in. And so after some simplification, you end up with this. A function of the outer variable x, 14/3 x cubed minus x to the 4th minus 1/3 x to the 6th. And so then we would do the outer integral. We take the antiderivative, and then we use the numerical limits of integration for the outer limit to, or outer integral, to get 216/35. That's the final answer there. So that's the volume under the x squared plus y squared curve. That's above this shaded region, right? So if you were to, make a 3D sketch, you've now got this shaded region here that looks like this. And you have some surface over here, which is x squared plus y squared, right? And so what we've just found is the volume that's underneath that portion of the surface that's right above this shaded region, the domain, okay? All right. Okay, but we could have chosen to use x as the integral on the inside. And if we did that, we would draw our domain sketch like we did before, but we would draw an arrow horizontally here first, which means that this boundary would now be have to be something where we're writing x as a function of the outside variable y. So we would be using this version of this boundary. X is 1/2 y as the starting value. It's the beginning of my arrow. And then x is the square root of y at the end of my arrow. So you always go from the start of the arrow to the end of the arrow, and the arrow has to point in the direction of increasing x. Same thing over here, increasing y. So same setup in the inside here, but since the x variable is on the inside, we have to use 1/2 y as the starting limit of integration, and the square root of y is the ending, right? Now we're integrating with x as the variable, so this is 1/3 x cubed. X squared is a constant times x, and then you plug this in first for all of the x's, and you plug this in then for all the x's. Uh, so this is the first version minus the second version, and after some simplification you get this, right? And then we would do integration again. So like this would be, when you add 1 to 3 halves, you get 5 halves. So it would be, 2/5 times y to the 5 halves, and then the 2/5 times the 1/3 gives 2/15. So this is the antiderivative of each of the terms, but then we're plugging in 4 and 0 in the copies. And we get that same 216 over 35, right? So you're free to choose whichever order you want, but we're always going to ask you to graph the domain and show with an arrow what direction you're using as the inner. And when you do that, that will help you get these limits right, that the right values are the starting and the ending. So the start value is the one with the lower number, right? And the ending value is at the end of the arrow where we have the upper number. Okay, so many times, like these, I would say were roughly the same level of difficulty, maybe a little easier integral to do on the left, right? But there are some times when there's a clear, better choice, right? If you have a region like this, let's say in the domain, right? If we integrate over y first, then that means we only need one integral, right? We've got x as, these are reversed. I think there's some typos in the notes here. So this would be y is a function of x, y is some function of x. So correct these in your notes if I haven't done that already. Y is some function of x. And so this would be a function of x, function of x, yeah. So you would be finding, you could find a function here and a function here and integrate that all in one piece, and then the x values can just be numbers from a to b, right? But if you decided to integrate over x first, then you would have, oh my gosh, these are all wrong. Let me just change those real quick. This would be x is some second function of y, x is some first function of y, and this would be x is some second function of y, and x is some first function of y. I'll try to fix those in the notes before we actually get to this lecture in the class. So the idea here is that because we don't have just one function for all the start values and one function for the end values, let me highlight that. All the starting values are here, all the ending values are here. Here, all the starting values are here, but I actually have two different ending values, one established for this and one established by this. And so I'm going to have to split the region in half and go start to end with this for this part, and then have a separate start to end for this part, right? So that would actually require two integrals, right? And I think these are reversed. These are y's here. Okay. All right, so sometimes there's a clear, better choice. And if you find that it's just really, really hard to do something, you can always try drawing the arrow in the other direction. In fact, sometimes they'll give you something that's filled out here, and it'll still be easier if you reverse that by graphing what you're given and then reversing that. We'll see an example of that coming up. Okay, one other thing before we just do some computations, you can actually use a volume structure to calculate two-dimensional area. If you have let's say you have a strange region here defined in some way, right? And you want to find the area, the two-dimensional area there, right? Well, we can use a double integral to find a volume. So if we just make the height equal to 1, then that volume in cubic units is actually the same number as the area is in square units, right? So if you just set the integrand to 1, the double integral will in fact give you a volume of 1 times the area, and numerically it actually gives you the area, right? So you can force a volume integral to give you an area calculation by making its height 1 to essentially remove that dimension. Okay, that's kind of nice if you're trying to prove what the volume is of different shapes, right? So many of the geometric volume functions are originally derived using this. Okay, let's just work some examples here. Here's one. We're taking the integral where they've defined everything. So I'm going to go ahead and draw the region. We're always going to draw the region just so that we can see what's going on. If I've got my x, y here, it looks like my y's are bounded by 0 and 4, right? And my x's are given by two functions, right? This function here is is x equals 0, and this function here is x equals the square root of y, right? Which, if I squared both sides, would be equivalent to y equals x squared, right? So essentially what I've got here is a parabola, right? I've got a parabola, y equals x squared. And then I've got a line, let's see, this is x equals 0. So x equals 0 would be this. Is that right? Yeah, x equals 0 would be this. Okay. And so let's see, if I'm bounded, and then I'm bounded from 0 to 4 in the y direction, right? So that means I'm not going to stray beyond that or here. So that to me looks like I'm covering this region, right? Looks like I need to fix something in my notes. Okay. All right, so if we're covering that region, what they're having me do is integrate x first. So my arrow would be integrating in the x direction, right? Just double check that this is the boundary y equals x squared, which is also x equals the square root of y. And we're integrating from x equals 0 here to x equals the square root of y, yep. And then we're integrating all of that from 0 to 4. Okay, so now I've got an idea of what we're doing. The reason I'm doing this is because it might turn out that it's going to be easier to change the direction of integration. I don't think it will in this case, though. So we'll just go ahead and carry this out as stated. So we're treating the x as the variable here. The y is just a constant, so I'll just keep it there, right? But the integral of x is 1/2 x squared, okay? And then we have to integrate that from 0 to the square root of y. All right, so I'm going to be plugging that into the x squared. In fact, sometimes what I'll do is, just to avoid plugging it in for the wrong variable, I'll keep the variable which is currently being held a constant outside. So if this y squared is really not the variable, I'll put it outside of my little bracket here and say I've got 1/2 x squared. That way I know when I'm plugging in, I'm plugging into the x, not to this y. Right, so I've got my constant out here, and then I've got 1/2, let's see, the square root of y squared minus 1/2 0 squared, right, by the fundamental theorem. And so the square root and the square will cancel, so I'm going to have 1/2, this is going to be y squared. Well, let me just draw this. There's 1/2, and there's a y squared times another y, so that would be y cubed. So the inner integral here produced 1/2 y cubed. Okay, so then I'll switch to the outer integral, right? The outer integral is 0 to 4 of that structure. Let me move the 1/2 outside, y cubed dy. And so that would be, I have my 1/2, I've got a 1/4, and then I've got y to the 4th from 0 to 4. Right, so that would be 1/8, and then we would be plugging 4 in. 4 to the 4th minus 0 to the 4th. And that turns out to be 32. Okay, so that would be that problem there. So in this case, it didn't help me to draw this out because I wasn't going to end up swapping things, because this was already pretty easy to do. Let's look at another example, and you can pause these videos and try these if you want. In fact, in the class, that's what I'm going to do. I'm going to go ahead and draw this out so we can see it. So we've got, let me draw it over here. We've got, let's see, we've got x and y, and we've got, this is x equals the cube root of y. And so that's the same as having, let's see, if I cube both sides, y equals x cubed, right, which has this sort of a general shape, right? Let me maybe switch colors here. Right, but since it was written this way, right, there's specifically no minus here, so it's not this part here, it's this part. Okay, here is y equals x cubed, or also could be x equals the cube root of y. And then the other one is x equals 2. X equals 2. So x equals 2 would be out here. That's a vertical line. Okay. So it seems like, and then I'm going in the other direction from 0 to 8 in the y direction. So from 0 to 8 up here in the y direction. And this is my region in here. I'll lightly shade it. Okay. Okay. Um, Let me go ahead and make a copy of that because I have a feeling we're going to have to change these things. I'm going to make a second copy just to demonstrate something. So maybe first we would try just the way it's actually written. X is first, right? We're actually doing this. This is what's written. We're going from the cube root to 2 in the x direction. And so let's try to do that integral. The inner integral here would be from the cube root of y to 2 e to the x to the fourth dx. Okay, so well, let's see. Unfortunately, let's see, I've got a composite function here. I could try a u sub. Let's try that. U equals x to the fourth. Therefore, du is going to be 4x cubed dx, right? And then that would make this e to the u, but then the dx would be 1 over 4x cubed du. And then I would have to figure out what this corresponding value is. But I can already see that this is not going to be easy, right? Because it's not easy for me to replace this x cubed when I just have an x to the fourth. So this is very difficult to do. It's possible that you might be able to find some integral in an integral table where somebody has worked this out, right? But this suggests that, hey, this is pretty hard. Maybe we could change the direction of integration. So what if I did that? If I change the direction of integration, my arrow would look like this, right? And then I would be saying, okay, let me make a new integral over here. We're going to say, we still have that e to the x to the fourth, but I'm going to put the y on the inside. Okay, so then that means we're going to be integrating from y equals 0 to this curve, which is y equals x cubed. So I will be integrating from y equals 0 to y equals x cubed. And then I would be integrating in the x direction from 0 to 2. Right, so that wasn't too hard to swap that. Okay, but that's going to make this much easier to integrate because this is a 4 here, not a y. Okay, if I do the inner integral now, I've got integral from 0 to x cubed of e to the x to the fourth dy, and this whole thing is a constant now. So this complicated thing that we were trying to deal with before is a constant just times the y from 0 to x cubed. So I've got my e x to the fourth, and then if I plug this in, I get x cubed minus 0. And so this is just x cubed e x to the fourth, right? And then that seems more complicated, but actually that's going to allow me to more easily do my outer integral. My outer integral is dx from 0 to 2. So from 0 to 2 of x cubed e to the x to the fourth dx. Well, now actually integration by substitution is going to work because I can see that when I take the derivative of this and get 4x cubed, the x cubed part's over there. So if I do a u sub where u is x to the fourth, then du is going to be 4x cubed dx. And then if I substitute here, I'm going to have e to the u, right? And then this x cubed dx here is going to be equal to 1/4 du. So I can write 1/4 out here du. And then let's see, let's figure out what the new limits of integration are. If I was going from 0 before, x to the 0 would be still 0, right? And if I was going to 2, u will be 2 to the fourth. 2 times 2 is 4, 4 times 4 is 16. And so this is now a really straightforward integral. There's my constant. The antiderivative of e to the x is the copy. And then I'm plugging in 0 and 16 here. So this is going to be 1/4 e to the 16 minus e to the 0. Maybe I'd write it one more way. 1/4 e to the 16 minus 1. Right? So not easy, but certainly more doable than this. Right? So this is changing the direction of integration, and you do that when it's advantageous, when it just you can't make any progress in one direction, or it just seems like it's too hard. You can always try the other method, right? It didn't look ahead of time like one of these was going to be better than the other, but this direction turned out to be much better. All right. Okay, let's do a couple more examples, and you can pause these and try them yourself. So you can always pause this, try it, and then I'll work it here in a second. All right, so in this case, I have this defined, right? I've got, let's use this to graph the region because they haven't established the order x, y for us. So let's graph it. And let's see. We've got y goes from y equals 0, which is horizontal line. And then y equals x squared is going to be this, right? But 0 stays between, or x stays between 0 and 1. So it looks like it's this region here. This is the region. Oops. Green one. Okay. And in fact, I don't need the rest of that curve. Let me get it off there. Okay. All right. So let's pick a direction. Doesn't really matter which one. Let's try up. Now, if we go up, that means we're going from the line y equals 0 to the curve y equals x squared. So these are going to be my limits of integration. So I would set this up this way. Y over x to the 5th plus 1. We're doing y first, right? Moving in the y direction, then x. And the limits would be from y equals 0 to y equals x squared. And then the x limits would be from 0 to 1. Okay. So let's see. The only thing in here that is, let's work on the inner one. The inner one, I'll write it again. This is really just one big constant, right? Because we're treating it as a constant while we're integrating y. Right, so basically what I have is the constant 1 over x to the 5th plus 1, and then I have 1/2 y squared. That's participating in the antiderivative from 0 to x squared. Right, so this is going to be that constant times this is going to be 1/2 x squared squared minus 1/2 0 squared times that same constant. So we're going to end up with 1 over x to the 5th plus 1. And then this is x to the 4th, so it's going to end up being 1/2 x to the 4th. So maybe I could put x to the 4th. I'll just put it beside it, x to the 4th. All right, then we have to integrate that with the outer integral. So for the outer integral, we're doing integral from 0 to 1 of that. So I have a 1/2. I'm going to put that outside. I've got 1 over x to the 5th plus 1, and then I've got x to the 4th dx. So we're taking this integral now of what resulted from the inner integral. Now that actually looks to me like something we can use u sub for, because if I take this whole denominator and make that u, then that means du dx is going to be 5x to the 4th, and so du is 5x to the 4th dx. That means that x to the 4th dx is 1/5 du. So I'm going to be able to substitute every little bit of this, right? Continuing this, we've got 1/2, and then the integral of this is 1 over u. And then this whole x to the 4th dx is 1/5 dx. So I'm going to bring that outside to join that. It's 1/10 integral of 1 over u d. Actually, this is du. But I need the new limits of integration. So if x is 0, then u would be 1. And if x is 1, then u will be 2. So now I'm evaluating this integral. The antiderivative of 1 over x is the natural log of the absolute value of u, evaluated from 1 to 2. So we'd have 1/10, and then natural log of 2 minus natural log of 1. But the natural log of 1 happens to be 0. So this is just 1/10 natural log of 2 is the final answer here. Okay. And that seemed pretty easy to do. I think I picked a direction which was fine. The other direction might be easier, might not be. This did require some u substitution. So let's just take a look at the other direction. Okay, I'm going to take the problem over again, and we'll just consider it from the other direction just to see. So, all right, graphing it again, I've got my x, y in the domain, y equals 0 to y equals x squared from 0 to 1 in the x. Okay, this is the region. And last time we went up. Let's say that we decided to go this way. So going from lower to higher x's, we would start here, right? But that means that we would have to change this curve to be in terms of x's. So this would be x is the square root of y, right? If y is x squared, it's plus or minus, but this is all places where x is positive. And then this would be the value x equals 1, right? So my integral now would be, we have y over x squared, x to the 5th plus 1, but I'm going to do the x direction first this time, okay? And then let's see, we're going from x is square root of y to x is 1, and then y has to go from, well, this is 0, but what is this? So I'm going to need the intersection of these two curves, right? So this is the curve y equals x squared, and the curve x equals 1, sorry. So if I plug x equals 1 in there, I'm going to get that y is 1 also. So it happens to be that this is also 0 and 1, although that could have been something else, right? Like if this had gone to 2, this would go up to 4, for example. All right, so now I start looking at this. Now the x is the variable. And unfortunately, I can see right now I have a problem, right? Because I have a denominator with x to the 5th in the bottom. There's no x to the 4th anywhere on here, like there was over here, right? Over here, I ended up producing the x to the 4th from the inside integral, so I was able to do substitution by parts. But that's not available to me now. So short of happening to find this in a table, I don't know how to integrate this, not easily. So this is not the right approach. We should stick with the other direction. Okay. All right, let's look at another example. So we have x cosine y over a two-dimensional region bounded by these three curves. Okay, so we'll just take however they decide to give it to us. We'll graph what they're telling us. So the line y equals 0 is the x-axis. The line y equals x squared is a parabola, potentially continues over here, and x equals 1 is this line here. Okay. And let's see, since this is y equals x squared, let's see, this would be 1 squared would also be 1. So I've got my boundaries here. It definitely looks like this kind of region over here again. And so I think I could pick either direction. You know what, though? When I have found in general that if you start on a constant and end on a function, often the integral works out a little nicer than if you start on an integral and end on a constant, or start on a function and end. So I'm going to choose to go this direction, but you can try it the other direction. We'll just do one direction. I think this is going to work out fine. So that means we're doing y first. Okay, so that means when we do our integral, we've got x cosine y. We're going to do y first and then x. Okay. So let's see. So we're going from y equals 0 down here. We have to use expressions in y. Y equals 0 to y equals x squared. And then the x will go from 0 to 1. All right, so let's look at the inner one. Integral from 0 to x squared of x cosine y dy. So the y is the variable, and that means that the x is just a constant. I'm going to keep it out of the antiderivative. The antiderivative of cosine is sine, so that would be sine of y. And then I'm just plugging in 0 and x squared, right? So that's going to end up being x, and then sine of x squared minus sine of 0, but sine of 0 is 0. So this ends up being x sine of x squared. Okay, not too bad so far. And then that will become the result of the inner integral. So for the outer integral, we're going to take integral from 0 to 1 of x sine of x squared dx. Seems like this is pretty concocted to work out, right? And a lot of these problems are going to be this way, because it would be very difficult for me to do sine of x squared directly if this x wasn't here, right? So I think I could just do u substitution, right? I could say, let's make x this inside function, because x squared is clearly inside of u, or inside the sine. So let's make that x squared, which means du dx will be 2x. Therefore, du is 2x dx. Therefore, x times dx is equal to 1/2 du. right? So now I can substitute everything here. I have sine of u now. The x dx part is 1/2 du. Let me write it again with the 1/2 brought outside. And I need my new limits. So if this is 0, 0 squared makes u also 0, and 1 squared is also 1. So they didn't change when I changed them to u's. Okay, the integral of cosine was sine. The integral of sine is negative cosine. So now I have the 1/2. The antiderivative is negative cosine of u with 0 and 1 plugged in. So I have a half, and I have a negative cosine of 1 minus a negative cosine of 0. Okay. Cosine of 0 is 1, actually. So I think we could write this as just negative 1/2 cosine 1, and then this would be plus a half. That'd be one way to write the answer. Okay. And I don't see any particular reason why the other one would be easier, so I'm going to stick with that. All right. I think the last thing I want to show you here is sometimes we just want to sketch the volume. So some problems will just ask you to reproduce what the shapes are. So let's first graph the domain. I always want to do that first because I can get that from the limits of integration. So, and then that will help me in graphing the three-dimensional shape that we're asking to be finding this of. All right, so let's see. This is y equals 0, that's this boundary, to y equals 1 minus x, right? So, well, y equals 0 would be a horizontal line. And then y equals, this is the same as negative x plus 1. So that's just y-intercept of 1, slope of negative 1. So that's going to be this right here. That's this boundary, y equals 1 minus x. And if we're going from this to this, we're covering this region in the domain. And then sure enough, this matches 0 to 1 in the x direction. All right, so given that, let me start making a three-dimensional because they're asking me for volume. Okay. We're just sketching here. So just translating that onto here, the region in the domain is this, right? This is the region in the domain. And so then this, which I'll do in red, this is the z, right? Z is 1 minus x minus y. Well, hopefully we could recognize that as a plane. So this is going to be some sort of a plane above this spot here. So one way to graph a plane, z equals 1 minus x minus y, is just use intercepts, right? So the x-intercept would be when y and z are 0. So if I put 0 in here and 0 in here, I'm going to get 0 equals 1 minus x, or x equals 1. So right, there's that. In fact, actually, I already know the x and y intercepts because they have to be right where that plane is. Well, maybe not. This happens to be x is 1. The y-intercept would be when x and z are set to 0. So this would be 0 equals 1 minus 0 minus y. Will also produce y equals 1. So with x and z 0, y is 1. And then the z-intercept would be when x and y are 0. Let's see, that would be z equals 1 minus 0 minus 0, so z is 1 as well. So actually up here. So there's these 3 points that are on this plane, right? So what we really have is a plane in three-dimensional space that's cutting into octant 1 like that. And so the volume is given by this region here. It's basically all the stuff that's underneath this surface between that and the xy plane, right? So that green volume in there that's bounded by all these edges, the coordinate planes like that. So that would be a sketch of the volume that this is finding. All right, and I think that's the last example. So things to keep in mind, just do the sketch for the domain, draw the arrow, right? This is the start of the arrow and the end of the arrow, right? Using this variable as that equals y equals 0, y equals 1 minus x. I think you should be good.